Okay, so I've drawn the circuit for Chapter 18, problem number 18, as they have drawn it in the book. But I want to make a couple of points real quick. First of all, this point right here, this point right here, this point here, this point here, this point here, this point here, all of those points could just as easily be labeled A. Because this entire wire here, this entire wire, is all at the same potential. Okay? Likewise, this entire wire over here, even though there's a junction, it's all at the same potential. So I can call that B, that's B, that's B, whatever. I'm going to add a couple more reference points here. Just point C and point D. Okay, I don't need to add another reference point, say here, because that's A. That's at the same potential as A, so I don't need another reference point in there. Remember that any connecting wire, that's a simple wire that connects, even if there's a junction, it's all at exactly the same potential. Now if there's a resistor in between 2 points on the wire, okay, those are at different potentials. Or if there's a battery between 2 points on the wire, those are at different potentials. But if it's just a plain old wire, then the potential's the same throughout the wire, even if there are junctions. Now, I also need to add currents. So I'm going to have a current up here on top that I call I1, current here on the bottom that I'm going to call I2, and a current here on the side, the middle branch that I'm going to call I3. Now, it doesn't matter in which direction these currents flow. I could have drawn I2 in either direction. And if I'm wrong about my guess, then I would just get a negative answer for I1, I2, or I3. But I've drawn them this way because typically positive current flows out of the positive terminal of the battery, right? So I've got I1 leaving the positive 12 battery, and I've got I2 leaving the positive terminal of the 8-volt battery. And then as far as I3 goes, well, I figure the push from I1 is going to be more, the push from I1 in the middle branch here, the push to the right from I1 is going to be greater than the push to the left from I2. So I'm guessing that I3 is going to point to the right. I could be wrong. Okay, so now we have to apply Kirchoff's rules, right? So we can start off with the junction rule. At that junction, I have I1 flowing in and I2 and I3 flowing out. Right? So the junction rule says that all the currents flowing in must equal all the currents flowing out. Now I got to do the loop rule. Okay, for the top loop, I'm going to go in this direction, and I'm going to consider the top loop only. All right. Now for that top loop, I'm going to do the following. I'm going to start at point A, and I'm going to go to point C. So I'm starting here, and I'm going over to here. And I'm going to take the potential difference. I'm going to take final minus initial. Okay, so there's VC minus VA. Next, I'm going to go from C to B, and I'm going to take final minus initial. And then I'm going to go from B back to A. Okay, final minus initial. The loop rule says that those have to sum to 0. Right? And they do. I got VC minus VC, I got minus VA plus VA, and I got VB minus VB. So it better sum to 0. Now if you look at figure 18.13 in your book, it tells you the sign conventions to use for these things. So let's start with VC minus VA. The voltage at C, the potential at C is going to be lower than the potential at A, right? Because A is at a positive potential and C is on the negative terminal of the battery. So VC minus VA, C is lower, so that's going to be minus 12. If I take VB minus VC, now the current is flowing this way through the resistor, and current flows from high potential to low potential. So that means VB minus VC is going to be high minus low. That's going to be plus 4I1. And then if I look at this resistor, resistor 2, the current's flowing to the right through that resistor, And so VA minus VB, that's going to be higher minus lower. So that's plus 2I3 equals 0. Okay? Now I'm going to consider the bottom loop. Okay, and I'm going to start, okay, for the bottom loop, I'm going to go around the bottom loop like this, and I'm going to start at the same place. I'm going to start at this junction over here, this junction over here at VA, and I'm going to go, what is that, clockwise? So I'm going to go from A to D. So final minus initial, and then I'm going to go from D to B, so final minus initial, and then I'm going to go from B to A, final minus initial. Okay? Now, so VD minus VA, that's going to be positive, right? D has a higher potential than A, so that's plus 8. Again, look at figure 18.13, and it'll tell you how you assign your signs. After a while, this becomes second nature, but it's useful to have that figure nearby for reference. Okay? Notice in that figure that they're always doing final minus initial. Read that figure caption carefully. The signs are everything. You mess up one sign and your problem is screwed. Okay, next we do VB minus VD. Now the current is flowing this way. Current flows from high to low, so that means D is higher than B. So it's low minus high, so this is minus 6I2. And then we already established that VA minus VB is plus 2I3 equals 0. Okay? So that's it. I mean, we're done with the physics. We've got now 3 equations, 3 unknowns. Here's equation number 1. Here's equation number 2. And here's equation number 3. Now you should attempt to solve these 3 equations algebraically and see what you get before you watch me solve them. So you should pause the video now. Okay. Let's see. So to solve this, I think what I'm going to do is I'm going to take this equation and I'm going to substitute it in there. So that means that this equation becomes minus 12 plus 4I2 plus 4I3 plus 2I3 equals 0. Right, so the 4I1 became 4I2 plus 4I3. Okay, well that's minus 12 plus 4I2 plus 6I3. Okay, so I've now combined these first 2 equations, and so now I'm going to take these 2 equations and combine them. Now the easiest way to do that is to do a little bit of math, right? So I'm going to take this, and I'm going to take this entire equation, I'm going to multiply by negative 3. If I do that, I get negative 24 plus 18I2 minus 6I3 equals 0. And now I can add these 2 equations together, and I get negative 36 plus 22I2 equals 0. And so I2 is 1.636 amps. Okay, now I can solve for anything. I guess I'll solve for I3. So I'm going to take this equation and I get minus 12 plus 4 times 1.636 plus 6I3 equals 0. That's minus 5.456 is equal to minus 6I3. So that means I3 is 0.908. And then I1 is equal to I2 plus I3, so I1 is 2.544 amps. Alright? From that, you can answer whatever you want. For example, if you want to know the current through the 2 ohm resistor, well, that's just I3. So that's 0.908 amps, and it points to the right. If you want to know what VB minus VA, well, you can, well, we've already got that, right? Well, this is VA minus VB up here we have VA minus VB is 2I3, so VB minus VA is minus 2I3. So that'd be minus 1.82 volts. Right? You can also check your work by looking at the outer loop. Right? In other words, you can do VC minus VA. Again, I'm starting at A, and I'm going around the outer loop in a clockwise direction, I guess. So I go from A to C, then I go from C to B. So I take final minus initial. And then I go to D, VD minus VB, and then I go back to A, VA minus VD. Alright, that's the outer loop. And that should also add up to 0, right? And it does. VC minus VA is minus 12. This is plus 4I1. This is plus 6I2. And this is minus 8 equals 0. And you can check that for yourself to see that it also adds up to 0. So that's a Kirchoff's law problem. I don't teach these normally when I teach the class, but they're good practice, very difficult logical problems. Let me know if you have any questions.